In a previous video, we talked about titrations, and we talked about acid and base titrations very generally. In this video, we're going to get into a lot more detail about different types of acid-base titrations and what they tell us about what's going on inside the titration mixture. The first and the simplest type that we're going to look at is strong acid, strong base titrations. So in this case, we're talking about a strong acid like HCl and a strong base like NaOH as an example. It's going to make water and a salt. If we split these up, they're strong, so we can break all the ions up. This is our ionic equation. We see that chloride's a spectator and sodium's a spectator. So the net ionic equation is just going to end up being the formation of water from the ions. Here we have a particular titration. We have 0.1 molar NaOH in the burette, and we have 25 milliliters of 0.1 molar HCl in the flask. Let's first of all figure out what's the equivalence point going to be at. This is just a stoichiometry problem is all this is. So we can go 25 milliliters, that's the volume of acid in the flask, and its concentration is 0.100 moles of H plus per liter, and there's 1 mole of OH minus for every 1 mole of H plus in the net ionic equation, and the concentration of the NaOH is 0.100 moles of OH minus for every liter. So everything cancels out here except for milliliters, and that's going to be the volume at the equivalence point, and that's going to be 25.00 milliliters. So when we have added 25 milliliters of the stuff from the burette, we have reached the equivalence point for this reaction. What we're going to do next is we're going to track the pH by calculations at a bunch of different points during the titration. The first thing that we want to look at is what's the pH at the start. So at the beginning, all we have is a strong acid. The major species in here are the H plus, and then the chloride ion, and then water. What contributes to pH is just going to be the H plus. Now, because HCl is monoprotic, and because it's a strong acid, the concentration of the HCl is going to be equal to the concentration of H plus initially, and that's going to give us our pH. So our pH is equal to the negative of the base 10 logarithm of the concentration, which is 0.100 molar. And so our pH is 1. That's before we add any NaOH. So after each one of these calculations, we're going to drop a dot on a graph of pH versus volume of OH added. So you can see we have our dot at 1 and 0 volume of OH. Now let's take a look at what the pH would be after 5 milliliters of OH minus are added. What are the major species that are going to be present here? We're going to have H plus in there. We're going to have H2O. We're going to have chloride ion from the acid. And we're going to have sodium ion from the base that we've added. Sodium and chloride don't have any effect on pH, neither does water. So the amount of H plus that's still there, that's going to be what influences our pH. So let's set up a BCA chart. The reaction that's going to be happening is H plus plus OH minus making H2O. And remember, this is a one-way reaction. Before, well, we have 25 milliliters at 0.1 mole per liter. So that means we have 2.50 millimoles of H plus. OH minus, we've added 5 milliliters, and it's also 0.1 molar, so that means we have 0.5 millimoles of OH minus. Don't care about water. The change, OH minus is the limiting reactant, so we're going to lose 0.50 millimoles of each. Still don't care about water. Afterwards, we won't have any OH minus in solution, but we'll have now 2 millimoles of H plus. So the concentration of H plus is going to be those 2 millimoles that are still there, that haven't reacted, divided by the volume. Well, we had 25 milliliters in there before. We added 5 milliliters, so now our volume is 30 milliliters. And this gives us a concentration of OH minus of 0.067. So that means the pH is the negative base 10 logarithm of 0.067, which is 1.17. So our pH has risen. because some of the H plus got used up. That reduces the H plus concentration, but also the volume has increased, and that also reduces the H plus concentration. It's still a strong acid, it's just not as strong as it was before. So now we have that new point added on there. It's a little bit higher than it was before. Let's look at the pH after 10 milliliters of OH minus has been added. The same thing has happened, it's just happened longer. So we can set up a pCA chart, H plus plus OH minus, making H2O. Initial, we started out with 2.50 millimoles. Hydroxide, at this point we have now added 1 millimole. This is before, not initial. Change, we're going to lose 1 millimole. Afterwards, this is now going to be 1.5. Won't be any OH minus. And so that means our concentration of H plus is 1.50 millimoles of H plus in what is now 35 milliliters. And that's a concentration of 0.043 molar. And if we take the negative base 10 logarithm of that, that gives us our pH, which is 1.37. So now it's gone up a little bit. So what we did here was, first of all, we took a BCA chart and we used that to find the number of moles of H plus that were still present. Then we used that and the new volume to find the H plus concentration. And then we used that to find the pH. Up until we hit the equivalence point, every additional volume of OH minus added is just going to make a weaker acid by this same strategy. So let's just step through. This is 10 milliliters, 15, 20, 24. We're getting close to the equivalence point, so we're going to make the additional volume added a little bit smaller. 24.5, 24.75, 24.9, 24.99, and now we've reached the equivalence point at 25.0. What's present in the solution now? We have now used up all the H plus. If you do a BCA chart, neither one will be the limiting reactant. There's just as many moles of OH minus have been added as there were H plus in the original solution. So that means we just have the two spectators, sodium and chloride ions, and water, and the pH of water is 7. Because remember, cations from strong bases and anions from strong acids do not affect pH. So it's just the pH of water, that's 7 if it's 25 degrees. So putting that on the chart, here's our equivalence point, sitting right at 7. Now, at 25.01 milliliters of OH minus added, we are now in a different zone. This is not a strong acid anymore. We have used up all the H plus, and now we're starting to put in a little more OH minus. So we actually have a strong base present. Let's figure out what the concentration of OH minus is, and then use that to figure out our pH. So a BCA chart would be useful. It's the same reaction, H plus plus OH minus, making water. And our before was, this was 2.50 millimoles. We have now added 2.501 millimoles of OH minus. The change, now the limiting reactant is the H plus. So we're going to lose 2.50 moles of each, so that afterwards we don't have any H plus, but we still have 0.001 millimoles of OH minus present. So the concentration of OH minus is 0.001 millimoles, and now the volume is the original 25 milliliters plus the 25.01 that we added, so we're at 50.01 milliliters. And this is 2 times 10 to the negative 5. That's the concentration of OH minus. If we take the negative base 10 logarithm of that, we get the pOH, which is 4.70. And so pH is 14 minus 4.70, which is 9.30. Strategy here was we used the BCA chart, and we used that to figure out the number of moles of OH minus that were present, and then we used that with the new volume to figure out the concentration of OH minus, and then we used that to figure out the pOH, and then we used that to figure out the pH by subtracting from 14. We can continue to do that now as we add additional base from the burette, because it continues to be a strong base, it's just getting stronger. So there's the new point. It's quite a bit higher than 7 actually. There's quite a large jump with that extra 100th of a milliliter added in pH. Just like there was a big jump when we added the last 100th of a milliliter from 24.99. So there's a huge steep increase in pH with very little volume added at the equivalence point. After 25.10 milliliters added, that's what we get. After 25.10 milliliters added, 25.25, 25.50, 26, 30, 35, 40, 45, and we'll stop at 50. So you can see that the pH rises in kind of a linear fashion from a very low pH, and then as it gets near the equivalence point, it shoots up very steeply, and then after the equivalence point, it starts to taper off, continuing to get higher pH, but not at as quick a rate as it did near the equivalence point. Now let's look at a weak acid strong base titration. This is a reaction that's going to occur in this particular example where acetic acid is reacting with NaOH. You can split up the Na and the OH. Spectra, what we have here is Na+, so the net ionic equation is just the acid reacting with OH- to make water and its conjugate base. Let's analyze this titration as well. First of all, let's figure out what the equivalence point is. So we have in the flask 25.00 milliliters of our acid. The acid is 0.10 moles of acetic acid per liter. It's 1-to-1 stoichiometry. 1 mole of acetic acid goes with 1 mole of OH-, and the concentration of the OH-, just like in the last example, was 0.10 moles of OH- per liter. And so this comes out to 25 milliliters again. So when we reach the equivalence point, that'll be 25 milliliters. Let's look at what is the pH at the start. The major species that are present, we haven't added any NaOH yet. The only thing that's in the flask is acetic acid and water. The only thing that can influence pH there is going to be the acetic acid. Because this is a weak acid, we can use a rice chart to figure out what is the H+ concentration and then use that to get pH. So the reaction, HC2H3O2, ionizing to give H+ plus C2H3O2 1-. That's what weak acids do. And then the initial concentration was 0.10 moles per liter. None of this before ionization. The change, minus X plus X plus X. At equilibrium, 0.10 minus X. This will be X and so will this. So our Ka, which is 1.8 times 10 to the negative 5, is equal to H+ concentration, which is X, times concentration of the weak base, which is also X, divided by 0.10 minus X. So we can solve for X. You can make a simplification here if you want to. If you don't want to, it's fine too. X is the concentration of H+ in our chart, and that is 0.0013 molar. So we take the negative base 10 logarithm of that to get pH, and the pH here is 2.87. So that's before any NaOH has been added at all. Looking at that on the graph, it's a little higher than our previous titration, and which makes sense because it's a weak acid, not a strong acid like in the last titration. Now let's take a look at what is the pH after 5 milliliters of OH- has been added. Now what's present here? We added some OH-, but not enough to use up all the acetic acid. So there's still going to be some acetic acid present, but we have also created some acetate ion. Acetate ion is the conjugate base of this acid. So we have an acid and its conjugate base in the same solution. That's a buffer. So the best way for us to find pH is we're going to take a BCA chart, and we're going to use that to figure out the number of moles of acetic acid. I'm going to just say HA for short. And also the number of moles of acetate ion. I'm just going to say A minus for short. And then we can use the Henderson-Hasselbalch equation to find pH. Now we know that Ka here is 1.8 times 10 to the negative 5. So pKa, which we'll need for the Henderson-Hasselbalch equation, is the negative base 10 logarithm of that, and that turns out to be 4.74. So we'll keep that in mind as we do this calculation. All right, so the reaction is HC2H3O2 with OH minus making H2O and C2H3O2 1 minus. Before, we have 25 milliliters of acetic acid, and it's 0.1 mole per liter, so that is 2.50 millimoles of acetic acid. We have just added 5 milliliters of OH minus at 0.1 moles per liter. That's 0.500 millimoles. Don't care about water. There isn't any acetate ion. Change. The limiting reactant is the OH minus. So we're going to lose 0.5 millimoles, and we're going to lose 0.5 millimoles here as well. We'll gain 0.5 millimoles of acetate ion, so that at the end we have 2.00, no OH minus, don't care about water, and 0 plus 0.5 is 0.5. So the number of moles of base is 0.5, the number of moles of acid is 2 in millimoles, and so pH, according to the Henderson-Hasselbalch equation, is pKa, which we just calculated is 4.74, plus the base 10 logarithm of base over acid moles, so 0.5 over 2, and this comes out to 4.14, so that's our pH. As long as we don't consume all of the acid and continue to produce base, we will continue to have a buffer. And so we can use the same strategy, BCA chart, to find the number of moles of acid and conjugate base, and then the Henderson-Hasselbalch equation to find pH. When will that not be the case anymore? At the equivalence point, because at the equivalence point we will just have used up all of the acid and we won't have that anymore. We would only have the weak base. So up until 25 milliliters, we can continue to use this strategy. I'm not going to go through all the calculations. We'll just look at what it does to the graph. There's the point for 5 milliliters added, 10 milliliters, 15 milliliters. What we can see here is there was a sharp increase, but then once the buffer gets formed, buffer's doing what buffers do, and that's resisting changes in pH. 20 milliliters, 24. Again, we're getting smaller increments as we get closer to the equivalence point. 24.5, 24.75, 24.90, 24.99. And if you look at where we're at, 7 is about here, maybe there. We're already above 7. So we are not at pH 7 at equivalence point like we were with strong acid, strong base. Now we're at 25 milliliters. What's present? At 25 milliliters, we don't have any acetic acid anymore. We've used it all up. We have sodium ions in there. They don't affect pH. We have water. That, of course, doesn't affect pH much. But we have a weak base present. So because we have a weak base, that's the only thing in there that can influence pH. We're going to have to use a Rice chart to figure this out. So here's our weak base, C2H3O2 1 minus. It's going to react with water, produce the conjugate acid, HC2H3O2, and some hydroxide ion, and that's what's going to influence pH. Initial concentration. Well, what is that initial concentration? The initial concentration of C2H3O2 1 minus is the number of moles of acetate ion divided by the total volume. Well, we have converted all 2.5 millimoles of acetic acid into acetate ion now, and our volume has increased up to 50 milliliters. So this is millimoles over milliliters, and that's a 0.050 molar concentration. So this is 0.050, don't care about water, none of this. Then there's the change, lose some moles of each of these, gains equivalent number of moles of each of these. At equilibrium, this is 0.050 minus x, this is x, and this is x. So Kb, which is going to be Kw divided by Ka, is equal to x squared over 0.050 minus x. When you take Kw divided by Ka, you end up with 5.6 times 10 to the negative 10th. And when you solve for x, which is concentration of OH minus, you get 5.3 times 10 to the negative 6 moles per liter. So POH is the negative base 10 logarithm of that, which is 5.28. So pH is 14 minus 5.28, which is 8.72. So that's the pH at the equivalence point. As we saw in the chart, it's higher than 7 at the equivalence point, and that's because you don't have water at the equivalence point. Now let's look at after 25.01 milliliters of OH minus has been added. So we're now 1/100th of a milliliter past the equivalence point. What are the major species now? Well, we have the spectator, which doesn't influence pH. We have a weak base, which influences pH a little bit. We have water that doesn't influence pH. And we have OH minus, a strong base, which influences pH a lot. So the thing that's going to matter the most is going to be the OH minus that's been added here. Why do we have OH minus present? Because we kept adding NaOH, but we no longer have any acid to use it up. Okay, so here's our strategy. We're going to take the BCA chart to figure out how many moles of OH minus are now in our solution. We're going to use that and the new volume to find the concentration of OH minus. Then we're going to use that to find the POH, and then we're going to subtract from 14, and that's going to give us our pH. So that's our strategy for finding pH in this new zone of the titration where we have a strong base present. So the reaction, acetic acid and hydroxide, making water and C2H3O21 minus. The before, remember we started out with 2.5 millimoles of acetic acid. We have now added 2.501 millimoles of OH minus because we have 25.01 milliliters at 0.1 mole per liter. So the change, acetic acid is now the limiting reactant. So we're losing 2.5 moles of each of those. We're adding 2.5 moles of weak base. Afterwards, no acid left. We now have 0.001 moles of OH minus, and we have 2.500 millimoles of acetate ion. So what's our concentration of OH minus from the strong base? It's 0.001 millimoles in our total volume, which is now 50.01 milliliters. So our OH minus concentration is 2 times 10 to the negative 5. If we take the negative base 10 log of that, that is POH, which is 4.70. And if we take 14 minus that, we get our pH, which is 9.30. Now, just to verify that it was okay to ignore the OH minus that's coming from the weak base, when we had at our equivalence point 2.5 millimoles in water, the concentration of OH minus was 5.3 times 10 to the negative 6th. It's now 10 to the minus 5, so roughly an order of magnitude higher concentration from the OH minus that's just been added after the equivalence point. So it is totally okay to ignore that because it's not going to make any difference in the total amount of OH minus. And that also means that from here on out we can use this same strategy. Make a BCA chart, figure out how many moles of OH minus are present, use that in the volume to find the concentration of OH minus, and then get the POH, and then get the pH. We can just continue to do that for the rest of this titration. So I'm not going to do the calculations, I'm just going to show you the results. 25.10 milliliters added, 25.25, 25.50, 26, 30, 35, 40, 45, and we'll stop at 50. If you look at this curve, after the equivalence point, it looks a lot like the curve that we had before. The reason for that is it's basically the same thing. We have the same concentrations of acid and base, and we have a strong base after the equivalence point in both cases. So here's a comparison. The green is the strong acid, strong base. The red is the weak acid, strong base. pH 7 is outlined here. We can see that the equivalence point is pH 7 for the green curve. That's the strong acid, strong base, but it's higher than pH 7 at the equivalence point for the weak acid, strong base. Those are your equivalence points compared with 7. Here's an interesting point that sometimes can be a shortcut in answering questions. When you're halfway to the equivalence point, the number of moles of your conjugate base is going to be equal to the number of moles of your conjugate acid because you've just used half of it up. So if that's the case, then that means this value is 1, log of 1 is 0, so that means the pH equals the pKa when you're halfway to the equivalence point in a weak acid, strong base titration. We're not going to go through all the details for this next one, but a strong base, strong acid is just a kind of a mirror image of a strong acid, strong base. So in this case, we have sodium hydroxide in the flask, HCl is in the burette, the pH starts out high, it's a strong base all the way to the equivalence point, it just gets less and less strong. The equivalence point is at 7, and then it's a strong acid after that, and it continues to get stronger, but it has that same sort of a decreasing change in strength that we saw in the strong acid, strong base titration. Weak base, strong acid, once again, it's kind of a mirror image. Here's an example. If we have ammonia, a weak base in the flask, and we have HCl in the burette, the pH starts out high, but not as high as if we had a strong base. We create a buffer because we're going to create the conjugate acid, and it's going to be present with the base until you get to the equivalence point. So this is a buffer region right here. And then when you get to the equivalence point, your pH is going to be below 7 because now you have used up all of the weak base, and the only thing that's in your solution at the equivalence point is the conjugate acid, so it's a weak acid solution. Then after that, it becomes a strong acid as the added H plus is just going to be dominating the pH situation. Polyprotic acids. I think we've talked about this in a previous video, but a polyprotic acid has more than one ionizable proton. For example, H2CO3 is diprotic. The first thing that happens is H2CO3 becomes HCO3 and releases one proton. That has a Ka, but then HCO3 is also an acid, and it can give up another proton and produce ultimately CO3 and that has a Ka. Look at the values of Ka. One is 10 to the minus 7th, the other one is 10 to the minus 11th. That second ionization produces way less H plus than the first one did. Here's another example. This is a triprotic acid. The first ionization produces one proton. Ka is 10 to the minus 3. The second ionization produces the second proton. 10 to the minus 8th is the Ka value. And the third ionization, 10 to the minus 13th, is the Ka value. So the bottom line is most of the H plus comes from the first ionization in these polyprotic acids. When you titrate a polyprotic acid with a strong base, it's a very similar situation, except you're going to have two equivalence points. The first equivalence point is when you use up the first protonation. So in this case, this is H2CO3. So at this equivalence point here, you have used up all the H2CO3 and produced HCO3 That's the major species. And then in that second ionization, you're going from HCO3 to CO3 and you've just used up all the HCO3 at that point. Now this is an idealized situation. It's not always quite that clean, when you actually do these titrations. But the curve does have more than one equivalence point. Here's a set of real titration curves that were taken using a pH probe and some graphing software in our lab. The red curve is HCl and NaOH. That's a strong acid, strong base. And you can see that long, flat pH low, long, flat curve, sharp increase centered around pH 7, and then a strong base after that. And then the blue one on here is acetic acid and NaOH. Starts with a higher pH, steep rise, then the buffer sets up, so it gradually changes. Then there's a sharp increase. Equivalence point is above pH 7. Then after that, it pretty much mimics the strong base, strong acid curve. Sodium hydroxide versus HCl, that's the green one. It's almost a mirror image of the HCl and NaOH curve. It's a strong base in the flask, strong acid in the burette for that one. The yellow one is ammonia and HCl. Starts with a lower pH, sharp decrease, buffer system gets set up, equivalence point is below 7, and then it's a strong acid after that. And then the magenta curve on here is H2C2O4, which is oxalic acid against sodium hydroxide. It's a diprotic, and you can see there's one equivalence point. It's not quite as sharp as ideal. And then here's the second equivalence point. One final topic is acid-base indicators. Lots of times titrations are done with acid-base indicators, and these are just dyes that change color in different pH environments. And how it works is the dyes are actually acids, and their conjugate bases have a different color. Here's an example. Phenolphthalein is kind of a famous acid-base indicator. When it's in an acidic environment, it's got some H's there, two H's, and those are ionizable. If you put it in a basic environment, those H's disappear because they're going to react with OH minus, and it's going to change to this ion. This is pink in color, and this is colorless. And so when you see phenolphthalein turn pink, that's how you know that your system is primarily basic. So you can use these indicators to tell when you're at something called an endpoint that you hope is near your equivalence point, and then you can use that as a way of telling that you've reached your equivalence point. So how do we select an appropriate indicator for a titration? Well, the indicator is a weak acid. Let's call it HN, and you'll definitely see the base color when the conjugate base of this indicator is 10 times higher in concentration than the conjugate acid. You will definitely see the acid color when it's the other way around, when the acid form of the indicator is 10 times more concentrated than the base form. So let's use the Henderson-Hasselbalch equation to figure this out. What would be the pH when you would see the acid form? Well, it would be equal to the pKa for the indicator, because it's an acid, remember, so it's going to have a pKa, plus the base 10 logarithm of 1 over 10, because your acid is 10 times more concentrated than your base when you would see that. The log of 1/10 is -1, so that would be when the pH is equal to pKa minus 1. When would you see the acid? Well, that would be when the pH is equal to pKa plus the base 10 logarithm of 10 over 1. The log of 10 is 1, so that's pKa plus 1. So your color change is going to occur between pKa plus or minus 1. That's going to be where the range is that you would see the color change in a titration. Here's a whole bunch of indicators, and you can see not only where the color change is on the pH scale, that's across the top here, but you can also see what the colors are. So here's an example, methyl orange. Its pKa must be somewhere around 4 to 5, because the change range is centered right on that pH. Here's phenolphthalein that we were looking at earlier. 9 must be about its pKa, because between 8 and 10 is where we see it change from colorless to pink. Bromethymol blue is another kind of common indicator. 7, around 7 must be its pKa, because the change from the yellow acid color to the blue base color happens between, about 6, and 8. So this chart includes lots and lots of indicators, and you could use a chart like this, or the idea that pKa plus or minus 1 is where your color change is going to occur, to select what would be an appropriate acid-base indicator for your particular reaction. So let's say you were doing a strong acid, strong base, like the first titration that we looked at in our examples. Our pH was equal to 7 at the equivalence point. We want to pick an indicator that would give us a color change right about in that zone. So one of these indicators here would be good for that. Remember, the pH change was very sharp for a strong acid, strong base. In just a few hundredths of a milliliter, we changed pH over several pH points. So there's actually a lot of these would work fine for that titration. If we were doing a weak acid, strong base, like the acetic acid, sodium hydroxide example that we did secondly, we had a weak base at that equivalence point. So some of these indicators that would work for a strong acid, strong base wouldn't work anymore, and we'd want to cheat more towards this part of the scale, because we would estimate our equivalence point too early if we used an indicator that changed at pH equals 7.